Okay, hello and welcome to the video. My name is Wade Smith, and this video is about the real cause of type 2 supernovas, similar to the Crab Nebula supernova and the future Betelgeuse supernova. Um, so we know that from observations and from observing what's left of the crab that there's an iron core at some point near the end of the life of a star that it starts to build an iron core. Well, iron fusion is endothermic in and of itself. However, I discovered that under the right circumstances, some of the iron isotopes can in fact fuse with hydrogen, and it's still endothermic on step one of this reaction, but it produces an anti-neutron. An anti-neutron reacting with another particle is massively exothermic. In fact, about 100 times more exothermic than would be electron capture. So there was a team of scientists who won a Nobel for suggesting that electron capture was the means of supernova in the Crab Nebula supernova. And I fact checked this about 18 years ago whenever I was hanging around on physforum.com and phys.org.com, the two physics sites. And I did some math using a combination of calculus 2 and other differentials and so forth. I did math which showed that indeed an antimatter reaction is the only way to explain the Crab Nebula supernova. In fact, they suggested that a certain amount of the supernova's mass was missing. About a third of the mass of the system is actually missing when they study it today. And again, I did math, which found that about a third of the mass of the star was converted into pure energy and ejecting another third of the mass of the star into space, and then led to why it was visible for over a year to the naked eye from the Earth. Um, So, and the math on the brightness of the star as seen from the Earth works out with the antimatter equation. And so I could show the math for this on paper if I want to. Uh, I would have to rederive some of it, but it's not that hard to rederive it. But anyway, it turns out that you need 100 times more energy to do the supernova than what electron capture can produce. But antimatter produces just over 100 times as much energy as electron capture. So that explains where the missing mass of the Crab Nebula supernova went. And that more correctly explains type 2 supernovas. In addition to all of this, I also discovered that supernovas can happen at about 4 solar masses, not 8 solar masses, um, because the uh, I'm sorry, I should be able to say this, but Chandrasekhar, our limit of white dwarfs is about 1.42 to 1.44 solar masses. And that means that the core of a sun-like star up to 4 solar masses is forming a white dwarf in its core, which is made of carbon, nitrogen, and oxygen. And this core can be up to 1.44 solar masses. Well, in a 4 solar mass star, the core skips straight to 1.44 solar masses worth of carbon, nitrogen, and oxygen, and that is the limit. And then it explodes before you ever even knew there was a white dwarf. So I did math on that one as well. And that happens at the end of the red giant phase of a 4 solar mass star. And it just goes red giant. And then at the end of the red giant phase, it cooks itself, it explodes. Now, why they haven't seen one like this yet is because 4 solar mass stars have to age a lot longer than 10 or 16 or 20 solar mass stars before they explode. 4 solar mass stars burn for almost as long as the sun before they die. So that's possibly why they're very rare to see an explosion like that. But anyway, I shall be done with this video, and that would be a totally new type of supernova because it uses a different mechanism than type 2 supernovas. It's more related to type 1A supernovas. But anyway, I shall be ending the video now. And I might actually physically publish a paper on this again. I've done self-publish this one time, and nobody read it last time, but I'm going to try again.